Here are going to be some examples of how to draw Lewis structures for both covalent and ionic substances. We will begin with some covalent substances. I know this is covalent because calcium is a metal, fluorine's a nonmetal, lithium's a metal, sulfur's a nonmetal, making those ionic bonds. So ionic bonds are characterized by transferring of electrons. Our Lewis structures will show that transfer of electrons. Start by counting your valence electrons because Lewis structures show valence electrons. Calcium lives in group 2, fluorine's in 7. There's 2 copies. I know this just because I have them memorized, but you can find them in your periodic table. Fluorine happens to be in VII, which is group 7. Calcium's in group 2, II, so I can figure out my valence electrons like that. That makes a total of 16 valence electrons. Since calcium's the metal, it's going to donate its electrons to fluorine. And since fluorine happens to have 7 valence electrons, it needs to gain 1 of calcium's, and then since the second copy of fluorine is going to gain the other, calcium will donate 2 electrons. What it's going to look like is calcium is going to be in the middle, no electrons, making it a +2 ion. Fluorine is going to be on either side with 8 electrons, 1 of which came from calcium. That's a -1 charge because it gained 1. Also -1 charge because it gained 1. And that would be the ionic Lewis structure for calcium fluoride. Lithium lives in group 1. There's 2 copies. Sulfur lives in group 6, 1 copy for a total of 8. The atom that I have only 1 copy of will go in the middle. Now since sulfur has 6 valence electrons, it needs to get 2. Each lithium can donate 1. So after each donates 1, sulfur will now have 8. It's going to be in brackets. We're going to put the ion with electrons in brackets. And it has a -2 charge. Each lithium cation is going to go on flanking sides of the sulfur ion, sulfide. The next several examples will be covalent samples. So this is H2O water. Covalent happens to have shared electrons, so our picture is going to show shared electrons using lines. Hydrogen's in group 1, oxygen's in 6. There's 2 copies of hydrogen. This gives us 8 total valence electrons. You need to determine your central atom. You never pick hydrogen, so that leaves oxygen. And then attach the remaining atoms on either side with the shared pair of electrons. Since it's a shared pair, each line's worth 2, so 2, 4. Right now, these electrons belong to both atoms because they're sharing them. So right now, oxygen has 4 electrons. We like to make our central atom happy first. So that's 8 electrons, which means I've ran out of my electrons. I followed the octet rule, 1, 2, 3, 4 pairs. 4 times 2 is 8. And the duet rule, 2 and 2, so all atoms are happy. That's a good picture for water. Moving on, I have a fluorine molecule. Fluorine lives in 7, 2 copies, so 14. Each fluorine is going to be connected to the other using a single bond. Start with that. Since I've used 2 electrons, 14 minus 2 is 12. There's 2 atoms. If I divide those 12 electrons equally, it's 6 each, which would make sense because each one needs 6 to get to 8. So that's a good picture right there. CH2O. Carbon lives in 4. Hydrogen lives in 1, and there's 2 copies. Oxygen lives in 6. 1 times 2 is 2, plus 6 is 8, plus 2 more is 12. Central atom, you want to choose the most electropositive atom, which means far from fluorine. If you have carbon, choose carbon. So carbon is going to be your central atom. Connect the remaining atoms using single bonds. So I've used 6 electrons in my picture right now. I have 6 to go. I'm going to make my central atom happy. So there's 8. I have 4 to go. The last 4 will go on oxygen. However, I ran out of electrons before I gave oxygen an octet. My hydrogens are okay though because they have a duet. If you run out of electrons, you steal electrons from the central atom, so these go away and they become a double bond on the carbon oxygen. So those those carbon electrons went away. I'm going to just wipe them out to show that they are completely gone, and they've become more efficient by being a shared pair of electrons instead of a lone pair. Everyone still has octets and duets, and I've only used 12 electrons in my picture. pH 3. Phosphorus is in group 5, hydrogen's in group 1, and there's 3 copies. That gives me a total of 8 electrons I need to use. We never choose hydrogen in the middle, so phosphorus is in the middle. Connect the 3 remaining hydrogens. Remember that hydrogen only ever has a line attached to it. We'll never put dots on hydrogen. So I have 2, 4, 6 electrons in my picture. I have 8. I need 2 more in my picture. That's good because phosphorus right now only has 6, so it needs 2 more anyhow. That's a good picture for pH 3. We're going to add some difficulty to some of these problems with some charges. So nitrogen is in group 5, oxygen is in group 6, there's 3 copies. Now if I have a negative charge, that means I have additional electrons, which means I need to add electrons. If this would have been a positive charge, I ran out of electrons, or I gave one away, which means I need to subtract. 6 and 3 is 18, plus 5 is 23, plus 1 more is 24 electrons. I need to choose my central atom. Nitrogen's further left, so I'm going to choose nitrogen, connect my remaining atoms. So I've used 6 electrons, that means 18 left. Make my central atom happy, so that means 16 left. 16 divided by the 3 atoms, if I were to spread evenly, does not work very well, so I'm just going to add electrons up to 16 in pairs. 2, 4, 6, 8, 10, 12, 14, 16. So I just ran out of electrons. However, this oxygen on the left is not stable. It doesn't have 8. So we need to move these electrons, make a double bond right here. Those electrons are now gone. And that's a good picture. All of my atoms happen to have 8, an octet, and I've only used 24 valence electrons. Since this is a charged particle, we put it in square brackets so that that charge is applied to the whole particle. We have the carbonate anion. Okay, so again, we see that negative popping up. Carbon's in 4, oxygen is in 6, 3 copies. Because it's -2, we're going to add 2 more. 6 and 3 makes 18. Plus 2 more makes 20. Plus 4 is 24. So this is going to be a very similar picture. C is in the middle. If you have carbon, choose it. It's also the furthest left, far away from fluorine. Attach your 3 oxygens. We've used 6 electrons. That's 18 left. 2 more to make our central atom happy. Then I have 16 electrons left. I can't divide 16 into 3, or 3 can't go into 16 with a whole number, so I'm just going to add electrons until I run out. There's 12, 14, 16. Ran out of all my electrons. The right-hand side oxygen is not stable, so I need to take these electrons away and make them more efficient to make both atoms happy instead of only carbon happy. And that's a good picture. All right, here we have BF4. Boron lives in group 3. Fluorine lives in group 7. 4 copies. Since it's -1, we add 1 more. 7 and 4. 7 times 4 is 28. Plus 1 more makes 29. Plus 3 more is 32. Central atom, it's not going to be fluorine because that's the most electronegative, so it's going to be boron. Connect the 4 remaining fluorines. I've used 8 electrons, 2, 4, 6, 8. 32 minus 8 is 24. 6 goes into 24 4 times, and there's 4 fluorines, so that's good, because each fluorine needs 6 more. And then, since this is a -1 ion, we will put -1 charge. HCN. Hydrogen's in group 1, carbon's in 4, nitrogen is in 5, for a total of 10 valence electrons. Choose carbon if you have carbon normally. It's also the most electropositive, so that would make sense. Hydrogen only needs a duet, so it's set. I have 2 4 electrons in my picture so far. I have 10 total, leaving me 6. Make your central atom happy. 2 left. I go on nitrogen. I ran out of electrons, which means I need to make my lone pairs on my central atom more efficient. So I need to remove this one. Now I have 2 4 6 8 on carbon, but a 2 4 6 still on nitrogen, so I need to remove the bottom lone pair and make them more efficient. So now I'm drawing a triple bond at this point, and then the lone pairs on carbon go away. I have the chlorate ion. Chlorine happens to be in group 7. Oxygen is in group 6. There's 3 copies. And then -1 charge means I have to add an additional electron. In this case, 6 and 3 make 18, plus 1 makes 19, plus 7 makes 26 valence electrons. I'm going to put my chlorine in the middle. Now chlorine is a little bit less electronegative than oxygen, which is why chlorine goes in the middle. Okay, so I've used 6 electrons. That gives me 20 left. 2 on the chlorine to make it 8. Then I have 18. There's 3 oxygens, so 18 divided by 3 is 6 each, which makes sense because I need to add 6 more to get each to an octet. Then since this is a charged particle, put it into square brackets. Finally, CH2F2. Carbon's in 4. Hydrogen's in 1, and there's 2 copies. Fluorine's in 7, and there's 2 copies. 7 and 2 is 14, plus 2 more gives you 16, plus 4 more gives you 20. If you have carbon, that's going to be in the middle. Never hydrogen. Attach your remaining atoms. Now, because I have 2, 4, 6, 8 in my picture, I have 12 left. Hydrogen only needs a line attached to it. Fluorine still needs an octet. 12 divided by 2 fluorines, 6 each, which would make sense to get us to an octet. So that's how we draw the Lewis structures for all these molecules. The other thing we can talk about on this is something called resonance. Now, to have resonance, you have to have a multiple bond. You have to have either a triple or a double bond. It's going to also have to be a covalent Lewis structure, not ionic. So this one, no resonance, because no double or triple. This one's no resonance. This one might have resonance. It has the triple, but we have to ask ourselves, could I have moved this triple over onto the left or change this to a double and a double? The answer is no, because hydrogen can only take a duet. It can only take one bond, so this is also going to be no resonance. Moving to previous examples. This structure doesn't have resonance because there's no double bonds or triple bonds. This one has a double bond, so we might have resonance. Could I have also drawn this double bond on the bottom or on the left instead of on the right? And the answer to that is yes. So this is resonance. So in actuality, the combination picture of this and this, these would be the most accurate depictions if we were to show all three pictures of the carbonate ion all at once, because the carbonate ion is a combination of those three pictures. So this is yes resonance, which would mean that this example, double bond, could have moved onto the right or the bottom oxygen as well. So this would be yes resonance. Going back to previous examples, pH 3, no double bond or triple bond, so no resonance. We have a double here, but that double can't be moved to hydrogens, so this is no resonance. And then the fluorine, no resonance. And finally, on a previous example, we had H2O, which would be no resonance. Hope that helps.